Okay, good morning. Today we're going to continue on with Chapter 8, talking about not how magnetic fields can be produced by our nerves and muscle, but how you can stimulate them using magnetic fields. And then we're going to move on next class on Wednesday to Chapter 10. We're going to skip Chapter 9 and start Chapter 10, so you want to start reading that for next class. You have homework due on this Friday for Chapter 8, so we'll go over a few of those homework problems today. Then you should have everything you need. If people do have questions now, I can take them, but we'll talk about some of them today. And then definitely bring questions on Wednesday. Try to get an early start. Okay, and then Chapter 10, like I said, we're skipping Chapter 9. Chapter 10 is the last chapter. We'll spend several days on Chapter 10, and then it's review, and then it's the final. So we're getting close. Getting close to the end. Okay, so magnetic stimulation. It's often called transcranial magnetic stimulation, or TMS, when you're dealing with stimulating the brain. What's the idea is you want to make a painless and completely non-invasive way to stimulate the brain. That's the goal. Now, what are some of the uses for magnetic stimulation? Well, first of all, you can use it to diagnose diseases of the central motor system in the brain. Now, let's see what that means. First of all, peripheral nerves. If you have a disease of the peripheral nerves, you can just stimulate. Say you want to study the nerve, the median nerve in the arm, you stimulate the shoulder, you record at the hand. You can tell whether the action potential is slowed down or not, just without having to stimulate the brain at all. So it's not the peripheral nerves, it's the central nervous system that you really want to use magnetic stimulation for. And it's not the sensory system, because if you wanted to stimulate the sensory system, you could say poke a person's toe and measure with the electroencephalogram and record their response in their brain. So even though that's partly central nervous system, sensory system, you don't need to stimulate the brain. But for diseases of the central motor system, where you're sending signals from the brain to the rest of the body, you really need a way to stimulate those nerves. So that would be one example. Another example is during spinal cord surgery. Sometimes, believe it or not, when you have undergoing spinal cord surgery, you want to keep track of whether the spinal cord is being damaged by the surgical procedure. So you basically want a continuity detector. So you need to stimulate the brain and then see if the other muscles move. Well, one way people have done it in the past is to actually release the anesthesia from the patient, wake them up, ask them to move their foot. That's kind of a drastic way to analyze whether the spinal cord is still intact, but it's one way. Another way is to stimulate the brain directly using magnetic stimulation. Number 3 is studying plasticity. Originally, it was thought that the brain was pretty much fixed. It couldn't be changed, but it's been found that the brain can change and reconfigure as life changes. So, in other words, an amputee who might have lost a leg in battle, the neurons that control that leg are going to be reduced, and neurons that control other parts of the body will expand in the brain over time. And you can study that if you stimulate the brain. You can. I worked at National Institutes of Health, and they were studying all kinds of interesting cases. For instance, they had people who were recently blind, and then they studied how large an area in their brain was represented by their braille reading finger as they learned to read braille, and they could actually watch the brain expand to learn. So these kind of procedures, plasticity, are a big role of magnetic stimulation. And finally, it's used to treat depression. That use is perhaps not as established scientifically as some of these other uses are, but it seems there's a lot of clinical evidence that it can be used to treat depression. One thing that's always worried me is that when you use electrical stimulation, electroconvulsive therapy to treat depression, you really have to induce such a large electric field, put electrodes on the scalp, and just give big shocks to the brain, and you have to shock the brain so hard that you get a seizure. And then it's been shown that can often ultimately lead to improved moods and improved reduced depression. For some reason, magnetic stimulation doesn't seem to need the seizure to have the same effects. So it's a very useful for treating depression, but it's not quite as understood exactly what the mechanism is. So those are some of the things you want to do. Now, why don't you just stimulate using stimulation of the brain or any of these applications? So here's the air outside the body, and here's the scalp, the skull. There's the brain in here. This is the skull. Now, what you could do is you could put electrodes here and electrodes here, and just a voltage, maybe a switch that turns it on and off. This is transcranial electrical stimulation. And the problem with it is that, remember, the skull is high resistance, so most of the current gets shunted here through the scalp with its muscles and pain receptors, and only a little bit of it penetrates and gets down into the brain to stimulate the neurons. So what happens if you're trying to stimulate the brain, you end up getting very large currents in the scalp that can be painful. And not horribly painful. At NIH, you could get normal volunteers, so you pay money to undergo these treatments. And if you pay them enough, they will undergo this sort of electrical, transcranial electrical stimulation. You can use them to do studies. But you can't use like children, you can't use patients who are very sensitive to pain. So this doesn't work as well as you'd like. So what transcranial magnetic stimulation is, here's your scalp, skull, brain. You take a coil and you pass a current through it, a current pulse. And the coil produces a magnetic field. So you induce a magnetic field, which looks like something like this. And the magnetic field reaches inside the brain, and it's changing with time. So Faraday's law of induction says a changing magnetic field produces an electric field, and it induces currents. So this is just Faraday's law, just like a transformer works. You induce currents in the brain, and then it's those electrical currents that stimulate the neurons. And the reason it works better than transcranial electrical stimulation is because magnetic fields essentially pass straight through the skull. The magnetic properties of the skull are the same as the magnetic properties of water, and basically the same as the magnetic properties of air. There's no significant magnetic properties at all. So the magnetic field can reach down in the brain and then induce the electric fields. So there's some electric fields induced in the scalp, but they're just about the same size as the electric fields induced in the brain. Doesn't hurt as much. So I've had this done to me. And you can put the coil over my head, and they click it, and my thumb would twitch, and you kind of feel, I mean, it's not like you can't feel anything, but it's certainly not painful. It's just kind of weird to kind of feel a general click, and then watch your thumb twitching, and then move the coil around. They can move activate different muscles. So that's the idea with transcranial magnetic stimulation. So how big is this current? Usually, if you plotted the current in the coil versus time, you find it looks something like this. It goes up and down, and this is about 1 millisecond. So the whole thing's over in 1 or 2/10 of a millisecond. And the peak current here is on the order of 10 kiloamps. It's a huge current that you're passing through that coil. Gigantic current. But it only lasts a very short time, so that it doesn't burn the coil up, because it's just a quick current pulse. And this induces magnetic fields on the order of about 2 Tesla. So your magnetic field raises by a couple Tesla in 1/10 of a millisecond. So you're getting about 2 times 10 to the 4th Tesla per second. That's your rate of change of magnetic field, which is a very big change of magnetic field. So that's the reason this works. It works because you're dealing with stimuli that are sort of on the order of the length constant of the nerve axon, but it happens all very quickly. And you can try to do this then repetitively, say 60 times a second, but then you start worrying about the coil heating up and other effects. All right, so it's not the magnetic field itself that's doing the stimulation. It is the induced electric field. That's a little bit in general about magnetic stimulation. I want to try looking at one of the homework problems, unless people had questions in general about magnetic stimulation. Okay, yeah?
How do you target like one part of the brain to not affect like all other parts?
Well, that's a good question, because one of the whole goals is to try to get as much spatial resolution as possible. And the short answer is you can't get real good spatial resolution. You can't get, you know, a tenth of a millimeter resolution. Even a millimeter is probably beyond what you can have. But they've designed new coils, and there's a coil, instead of a circular coil, if you use a coil that looks like this. Let's see, I don't think I drew that right. Oh, coming up, and then around, and then down. So current comes up, and it's going up in the middle here, and then it comes up and it's going up in the middle there. So it's adding together. You get a large electric field right underneath that coil, that part of the coil. That's a figure of 8 coil. And with these coils, you can often get individual fingers to stimulate as you move the coil. But that's in part because if you look at the representation of your body parts on the brain, your hand has a huge representation over the brain. So that the fact you can get individual fingers is more of about the representation of the hand on the brain than it is about the spatial resolution of magnetic stimulation. By no means could you get individual toes, or really you almost get the whole leg with just one location. So you can move the coil around a little bit, and you can get sort of millimeters type spatial resolution with these, but you give up when you get completely non-invasive, painless, but you give up some spatial resolution in the process. And the only way to really get the space, you can't get much better spatial resolution with electrical because it gets smeared out by the skull. So really the only way to get better spatial resolution is to go in with electrodes and do deep brain stimulation, but then you're taking the skull off, and it's highly invasive. Okay, so let's imagine now what happens. Say you had a coil like this, and you stuck it over your arm, so you're stimulating along the arm. So here's the way the nerve went. I want to analyze that. So what we're going to do essentially is we're going to do problem 32 in your homework. 8:32. But problem 32 in the homework assumes an electric field along the path of the nerve that's going to be different than the one I do here in class. So essentially, the whole process of the problem is going to be the same. I'm just going to use a different example. So this should get you started at least on problem 8.32. And the part A is exactly the same. Part A is we're going to derive the cable equation. So this part I'm essentially doing in class. And if you remember, back from when we derived the cable equation, we found that if you have current going through the membrane, that's because the current along the axon changes with space. And we had an equation like this. Minus A, that's the axon radius over 2. And if your intracellular current changes along the x direction, you get a membrane current. That's the continuity of current equation. It's really Kirchhoff's node rule. And the membrane current is 2 parts: a capacitive current plus, we're going to just assume, a constant conductance, a conductive current. This will be true at least until the sodium channels start opening. So for weak stimuli, just like with the cable model, we assumed a constant conductance. Now here's the new thing. If you have intracellular current, which is over here, you're going to have a conductivity times the intracellular electric field. And there's 2 pieces of that. There's a minus dV, this is really intracellular, dx, but we're going to end up grounding the extracellular space like we did with the cable model, so the I's and M's are going to be basically the same. But there's also a piece of the electric field that can't be produced by an electrical potential. One thing about Faraday's law is it produces, changing magnetic field produces an electric field, and that changing magnetic field doesn't obey the law that is minus the gradient of a potential. It's a new piece that gets put in. So we're going to have to put it in by hand and just call this the x component of the electric field induced by the magnetic coil. So it's an extra piece. Then we're going to put these three together, and we're going to put this for Jm, we're going to put this, and for Ji, we're going to put all that. So what do we get? We get a minus A sigma over 2. I'm also going to divide through by G, because we've done this before, so I'm not going to do every step. And you're going to get a derivative of a derivative, so minus d squared v dx squared. I'll just write v without a subscript because we're going to ground the extracellular space, so the membrane potential is the same as the intracellular potential. And you have this term, plus, and here you have a derivative, so dex dx equals Jm, which is, I divided through by c, so c over g dv dt plus v. All right. Now what we're going to do is we're going to notice this term, we're going to bring to the other side, and we're going to say that lambda squared is a sigma over 2g, just like before, the length constant. And we're going to say a time constant is c over g. That's the RC time constant of the membrane. And what we end up getting now is a minus, and then you're going to get a lambda squared dex dx equals, this side, it's a minus and a minus gives you a plus, but I bring it to the other side, minus lambda squared d squared v dx squared plus tau dv dt plus v. Here's the cable equation for magnetic stimulation. It looks just like the cable equation that we derived before, except for this new term. Now remember when we were looking at electrical stimulation, we had a second derivative of the voltage over here, and we had called it the activating function. Well, there's now, you can think of this as the activating function for magnetic stimulation. To a rough approximation, if this term and this term is small, you just get the voltage induced across the membrane of the cell is this activating function. So what this says is you expect the signal to be largest where the electric field is changing most rapidly. Now if you looked at this coil, and here's the path of the nerve, so this is the x direction. This coil, the electric field is largest right here under the center. But that's not where you stimulate, because you stimulate where the electric field is changing the most. So it's large here, it's about 0 out there and out there. So it's changing, it's getting smaller right here, but because of this minus sign, you'd be depolarizing the cell here, and you'd be hyperpolarizing it down here. So you'd actually be getting stimulation right there during magnetic stimulation. It's not directly under the coil, it's off to one side. So this is some work that I worked on at NIH, and we wanted to test this. So we wanted to actually do an experimental test of this. So it's kind of hard to tell exactly where stimulation occurs. But one thing you could do is you can put the coil down, you can stimulate, and say you record from a muscle down here downstream. Record how long it takes, or how long between the stimulus and when the muscle responds. Then you flip the polarity, either by turning the coil over or just flipping a polarity switch on your stimulator. And now you depolarize here and hyperpolarize here. Depolarize, it's a shorter trip down to stimulate the muscle, so you should have a quicker response. So there should be a latency shift between these two polarities. And if you can measure that latency shift, you can actually determine where stimulation occurs. So we're going to try to do that. This is just like problem 32. So this would be parts B and C of problem 8.32. First of all, you have to know what the electric field distribution is produced by this coil. And that's what I just kind of make something up. And it's slightly different than what's made up in your homework problem. I'm going to say it's E0 b over x squared plus b squared square root. So, what's this going to look like? As a function of x. Well, where is this largest? Where is that function of largest? Anybody see? Yeah.
The origin.
It's largest the origin. If x is 0, this becomes just b squared square root. So b over b is 1. It becomes E0 at the origin. When x is big, this denominator gets large and it falls off. So this thing has kind of a bell-shaped curve. It's not a Gaussian, but it's sort of like a Gaussian. Looks like that. So the electric field is largest at the center. So then what really matters is dEx dx. So let's look where minus dEx dx is the biggest. Okay, right at the origin, it's flat. So there's no derivative. So it goes through 0. Here it becomes it's down. It's going down with x. So dx dx is negative, but there's a minus sign out here. So it goes up, and then eventually it becomes flat. And this becomes an odd function, so it looks something like this. This is what dx dx looks like. So you're going to get depolarization here, and you're going to get hyperpolarization here if you just say v looks like the activating function. So this is exactly what I had said before, but now you can kind of see, you can figure out where depolarization occurs. And then if you switch the polarity of the coil, all of a sudden this becomes depolarization and this becomes hyperpolarization, and you're stimulating here. So how are we going to figure out how far from the center depolarization occurs? What's our usual trick? We're going to set the slope to 0 and find where this occurs, and then so we can figure out where that stimulation occurs. So we have to take, basically we have to take, first of all we have to find out an expression for the activating function, and then we have to take the derivative of it, set it equal to 0. So first things first, dEx dx, that's just activating its function itself. What do you get here? You have an E0 and a B, and then you have this thing. It's the only thing that depends on x. It's x squared plus b squared all to the minus a half. So the derivative would be minus a half x squared plus b squared to the minus 3 halves times the derivative of the inside by the chain rule, 2x. And the 2's cancel, and you end up getting a minus sign, E0b, and you have x over x squared plus b squared to the 3 halves downstairs. That's essentially what this function is. So I've just derived that function. Now, what did we say we want to do to find the peak? We take a derivative of that. So ddx of dEx dx, and we set it to 0. And when you're taking derivatives and setting it to 0, you can get rid of all these constants out front because you just divide through by them, and 0 divided by them is still 0. So all we really have to do is take the derivative of x over x squared plus b squared to the 3 halves and set that equal to 0. Okay. There's a product rule involved. There's x times x squared plus b squared to the minus 3 halves. So, there's also a equal sign missing there. It's 0 equals this. So we're going to have to set, let's do the easy one first. Let's take the derivative of this times that. And what do you get with that? Anybody should be able to do that one. Derivative of x. 1. So you just get 1 derivative of this times this. 1 over x squared plus b squared to the 3 halves. But now we got to take this times the derivative of this, and this is the harder part. What's the derivative of x squared plus b squared to the minus 3/2?
Negative 3/2 x times x squared plus b squared to the negative 5/2.
Okay, so I'll put it downstairs. And you said there was x, that's from this one, x times the derivative of that. And what else? There's the derivative of the inside, the chain rule, so you get 2x times 2x because you got x squared. So 2, and now this becomes an x squared. 1x is from the chain rule, and 1x is because of this in the product rule. All right, so that looks a little complicated now because it's got all these 3/2 and 5/2. What's the best way to simplify this? Anybody have a suggestion? Somebody's got it. Pardon? Okay, common denominator, but even better, let's just get rid of all this junk in the denominator. Let's multiply the whole thing by x squared plus b squared to the 5/2. Now we get rid of this denominator completely because that's upstairs and this is downstairs. Let's see what happens here. So this is going to be this term, the 2's will cancel, and you'll get a minus 3x squared, and this will cancel that. How about this term? This is going to be x squared plus b squared to the 5/2 divided by x squared plus b squared to the 3/2. So that's just x squared plus b squared to the 2/2, or 1. That's just x squared plus b squared equals 0. And now, all of a sudden, we're on track to solving this. Remember, we're trying to solve it for x and find out where this happens. So that's x squared minus 3x squared. That's minus 2x squared. I'll move it over here. 2x squared equals b squared. X is equal to b over square root of 2. And now we know exactly where this happens. And we also know where this happens. X equals minus b over square root of 2. So the difference, this is something like similar to what you did in the homework problem, the extra distance it has to propagate for one polarity than the other is going to be twice that. So delta x will be 2b over square root of 2. Or in other words, 2 is just square root of 2 times square root of 2. It's going to be square root of 2 times b. Now, suppose we know that the action potential is propagating with a speed given by u. Well, then we know u is delta x over delta t, where t is the extra delay. And if what we want is the extra delay, we can find that by going delta x, which is square root of 2b over u. So, what we find is that if you know the distribution of the electric field and you know the speed, you can find this delay that gets induced by switching the polarity of the stimulator around. And you can actually do that experiment, and we did it in a person's arm, and the median nerve in the arm, and we put the coil and we stimulated it, and we flipped the coil over and stimulated it, and it came out to be about a millisecond of delay, which is easily measurable. It's not real big, but it's easily measurable for these experiments. And so this separation, usually these coils are kind of largish, like this big. So we're talking about a couple, 2 or 3 centimeters, talking an inch from the center that it's stimulating at, an inch or so from the center. So what you have to do in problem 32 is you take a different electric field distribution. It's going to have the same general shape, but it's not going to have this exact form. And you're going to get the activating function, find where it's maximum, and just calculate. You're given the speed, you're given what the value of b is, so you just have to calculate what delta t is in that case. And that's an example of peripheral nerve stimulation using magnetic stimulation. Now, this is not necessarily the case in the brain, Because in the brain, instead of having long, straight fibers, you have fibers that are bending and twisting and getting larger and branching. And so there's a whole lot of opportunities for stimulation. And oftentimes you'll stimulate where the electric field is largest because of all that branching and bending. But in a long, straight peripheral nerve, you get stimulation at the activating function. Okay. Questions on problem 8.32 on what you're going to do? Like I said, you're going to do almost exactly the same thing, but this is going to be a little different. Okay. All right, then let's go on and talk about some of the other homework problems. So, this. Now let's talk a little bit about problem 27. Also in your homework, so I won't work the whole thing out, but I want to get it started. And this is a problem also about Faraday's law of induction. So we're going to be studying induced currents. But in this problem, we're going to study currents induced in an electrode that you might use to measure electroencephalography. And I'll tell you the motivation for this problem. I'm working at NIH, and a guy from, I think, Brazil comes along, and he arrives at NIH as a postdoc, and he says to me, you know, we were doing some experiments back in Brazil where we put electrodes all over the brain, and then we'd apply magnetic stimulation and use the electrodes to measure the response of the brain, and sometimes we'd actually burn the patient right under the electrode. Okay, so what's going on here? Well, they're inducing electrical currents by Faraday's law of induction in the electrode. But the electrode has usually there's a silver electrodes. Their electrical conductivity is maybe 10 million times higher than the electrical conductivity in the brain, in the scalp or skull or brain. Therefore, you get a lot larger electrical currents flowing, a lot more joule heating. Joule heating is negligible in the body during this, but joule heating in the electrode can actually be significant. And in fact, what they were really doing is they were stimulating using rapid rate, trying to stimulate like 60 times a second. Bing, 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 bing. And all those stimuli would add up, and they could get so high that the electrode temperature would raise high enough that they could see a burn. So as soon as they saw one, of course, they were more careful. But so the question is, how much electric fields and power is lost, and how much temperature increase do you expect in an electrode when you're inducing by magnetic stimulation? So we'll start with Faraday's law. Faraday's law, we used it and we just stated it in words. A changing magnetic field induces electric field. But if you write it down mathematically, you get that an electric field, if you take the electric field and you integrate it as a line integral in a closed loop, that's equal to the rate of change of the magnetic flux. So magnetic flux is magnetic field times area. The area might be constant, so you get dB dt, change in magnetic field with respect to time. So that's Faraday's law of induction. And just like when we used Ampere's law, we had a similar law. Ampere's law was magnetic field integrated around the path is equal to mu naught times the current density. Well, this is electric field integrated around the path is A times dB dt. So let's just take a simple example. Here's our electrode from the top view looking down. And it's going to have a radius A. And we're going to try to figure out what the electric field is throughout that electrode when there's a magnetic field coming out of the board that's changing with time. So let's look at some distance out here, r, and r will vary throughout the electrode. And what we're going to do is we're going to apply Faraday's law. So this is basically the electric field is going to go in circles around inside the electrode. So everywhere E will be parallel to this circular path. So this will turn into just E times the path length, or the length of this dashed line, which is just the circumference. 2 pi r. And that should look very similar to when we did Ampere's law with the magnetic field. This is going to be minus, and this is the area inside the dashed line, which is pi r squared. And then you get dB dt. So we're going to say that we apply some rate of change in the magnetic field, and you want to calculate what the electric field is. So electric field is easy because you just divide through, the pi's cancel. One of the r's cancel. There's r squared and there's r. So you get r over 2, and you get a dB dt. It's the electric field. And this is actually equation given in the chapter. Okay, so if part A wants to know what the electric field is, it's a function of r. It's 0 right at the center and gets stronger as you get out towards the edge. Current density. How would you get the current density if you know the electric field? It's just the conductivity times the electric field. So the current density is going to be also 0 at the center and gets stronger at the edge. But this conductivity is the conductivity of the metal that the electrode's made out of. So silver, I think, in the example. So now you know E times J. So that's part A of the problem. Part D of the problem says you can get joule heating. When you have currents flowing, you can heat things up. And the amount of the rate of heating, so the rate of energy put in, per unit volume, is going to equal, and this is given in the problem, E times J. So it's kind of like power in electrical current. Power in an electrical circuit is current times the voltage. Well, that's sort of the same thing here. Current density times voltage gradient to give you E times J. So what you want to do now is, if you want to know what the total amount of heating is for one magnetic stimulation pulse, what you have to do is this is per unit volume, you have to integrate over the volume. And then, since that's a rate, you'd have to multiply by the duration of the pulse. Now the problem is, this is what happens in this homework problem every semester, is some people will just take their results from here, multiply them together, and multiply by the volume of the electrode. It's not bad, it's a decent approximation. The problem is that E and J both depend on R. So there's 0 at the inside and a maximum at the edge. So what you really have to do is you have to integrate EJ dV to get the total rate. And then this becomes the rate of heating. And if you multiply that by the time, the delta T of the pulse, you'll get the total amount of heat put into that, or total amount of energy deposited into the electrode. So this is going to be E times J, which you got in part A. To integrate over the volume, well, this electrode really is, it's like this. It's got some thickness to it. Nothing depends on the depth. So the dV has a term that's just the thickness. But then you have to integrate over the cross-sectional area. So that requires a little bit more complicated thing. You end up integrating one of these things. The electric fields depend only on R. So if you integrate in little strips like this, this is going to have a thickness dr and a radius r. So dV becomes, let's see, a thickness of the entire electrode times 2 pi integral 0 to A, you're integrating from 0 out to A, of E, J, and this is R. There's the 2 pi R dr. So you end up integrating something like this, doing this integral. And that, when you multiply by the thickness and the time duration of the pulse, will give you how much heat is deposited in the electrode for each magnetic stimulation pulse. And then you're asked how much does the temperature of the electrode heat up. How would you get how much the temperature of the electrode heats up? How is that related to the energy deposited in there?
By the specific heat of the electrode.
By the specific heat, right. So you're given some information so you can calculate the heat capacity of the electrode, which is basically the specific heat, and involves the specific heat's per unit mass, so then you get the mass of the electrode, which is the density times its volume. So you can calculate the temperature increase for each stimulus pulse. And that is what your final answer is. You're asked to find how much this electrode heats up. And the answer I'll just kind of give you order of magnitude what to expect so you can kind of tell if you're on the right track. It's about 1/2 degree Celsius for each stimulus. Not enough to cause a burn, but not tiny. And if you started stimulating 60 times a second, these are going to add up and you could actually get some damage. So it's an example of Faraday's law of induction, which isn't really important for the body, because in the body, this conductivity would be really small and you wouldn't get significant heating. But if you stick some metal in there, all of a sudden you can get much higher temperature increases. If you happen to have a pacemaker and you did this, you might get currents induced in your pacemaker. So you got to be careful when a body has some high conductivity metal in it, that you don't. Be careful with magnetic stimulation. You have to be careful with magnetic resonance imaging. Anything that has changing magnetic fields could cause this sort of heating or disrupt the system. That is problem 27. Okay, you guys are going to be doing these problems, so if you have any questions, ask them now while we're thinking about it. Okay. Now, next problem is problem 28, which is sort of a sequel to this problem. So I'm about to erase all this. You can calculate this delta T from problem 27. Now, the nice thing about some of these problems in this homework assignment is the problem almost walks you through all of what's happening. But the bad news is it's kind of a complicated path you have to walk through. So suppose you find that each stimulus raises the temperature amount delta T. Now suppose you do rapid rate magnetic stimulation. What's going to happen? If you look at the temperature of the electrode as a function of time, and you're applying, and these stimuli are so short that on this scale, the actual time the stimulus on is almost instantaneous. So here, before you start, you're sitting at your sort of standard temperature, whatever that is, and then you stimulate and you raise the temperature up by amount delta T by applying the stimulus. What's going to happen after that? Well, it's going to begin to cool off. And it's to a pretty good approximation, it's cooling off by Newton's law of cooling. So it begins to fall off exponentially, like this. But after it goes a little ways, you stimulate again, because you're doing rapid rate stimulation. And you go up another delta T, and this begins to fall off. And then you're going to stimulate again. And you eventually get to a situation where you sort of reach steady state, where you're going up and down like this. And the question wants you to analyze and figure out how much total temperature increase is there. So after a long time, what's this temperature increase? I'll call this delta T. I don't think it gave it a special name. I just called it T in the problem. Okay. So you have to figure this one out. Well, what you do is you start adding up the results. So say at this time right here, this stimulus is going to give you an amount T. This stimulus gave you an amount T, but some of it had decayed away. So if it's falling exponentially, and if the time between successive stimuli is delta little t, that's the time between each stimulus, this would be minus delta t over some time constant tau that characterizes how fast cooling takes place. So this one, the contribution to the temperature at this time really depends on how this one's falling off, decaying. How about the contribution of this one? What's also cooling, but it's twice as long to cool. So you get plus T. I guess all of these should be delta T. This is the time. This is the temperature increase from 1. You get a temperature increase delta T times e to the minus 2 delta little t over tau, and so on. And this is a series, and it goes on to infinity, but it'll eventually converge, and you'll get the total increase in temperature. So now, the thing you want to do, and that's all equal to what we're calling big T, the temperature increase. Now there's a trick, and the problem has you go through this trick. I will take you through the quick ways. We're going to factor out the delta T. This becomes 1 plus e to the minus delta T over tau plus e to the minus 2 delta T over tau plus dot dot dot. And you can either make this go to infinity, or you can make, if you analyze just n pulses, you could have this end at some after n pulses. Okay, does anybody know the trick that we're going to do next? This is the thing that makes this problem solvable. You got an infinite series, so for the most part, that's kind of difficult to handle. But I'll give you a hint. The problem gives you, it tells you something similar to this: 1 plus x squared plus dot 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 equals 1 over 1 minus x. I believe that's the infinite series in this problem. Let me just make sure I'm on the right track here. 28. It gives you the result after n pulses, but if you take n to infinity, you get something that looks like that. So how are you going to use this? Well, the amazing thing is, this is a property exponential. This becomes 1 plus e to the minus delta t over tau plus e to the minus delta t over tau squared plus dot dot dot. You see, e to the minus 2 delta t over tau is the same as e to the minus delta t over tau quantity squared. E to the minus 3 delta t over tau is that cube. So what you end up getting is you just define this thing as x, and you have now that exact series, which you can solve, and you can figure out the total temperature increase. So in problem 27, like I said, you're guided straight through it, but the real trick is that you use this trick right here, property exponentials, to get it into a form that we know how to solve. Does anybody know how you get this? You can take it for the problem. It's just a given. But it's kind of a famous series. I'll show you how it's solved. You call this series, let's call it I. 1 plus x squared plus dot dot dot. Then you take x times I. So you get 1, so that becomes x. And you get x times x becomes x squared plus x squared times x is x cubed, dot dot dot. And then you subtract the two. I minus x times I equals 1, and all these terms cancel pairwise, and you end up getting, now solve for I, 1 over 1 minus x, and there you have it. So it's pretty cool thing. It was originally figured out by Gauss. If you do the finite case, Gauss was a famous mathematician, and he's in, I think, 3rd grade or something like that. And his teacher, his math teacher, wanted just to get the class to shut up and work on something so he could go do something else for a few minutes. So he told the class to add up all the numbers between 1 and 100. And basically, all the other students started adding 1 plus 2 is 3, plus 3 is 6. Gauss used basically a formula like this. He was able to, essentially he took 1 plus 2 plus 3 plus 4 plus 5, and he took 100 plus 99 plus 98 plus 97 plus 96, and then he was able to add them pairwise and find out that they all gave the same sum, individual terms, Anyways, Gauss figured it out in about 30 seconds, and he went up to his teacher and he gave the teacher the answer, and the teacher wasn't particularly happy with Gauss. But this all goes back to Gauss's analysis that he made when he was a little kid. But that's problem 20. Actually, that's problem 28. I forgot to change the number when I did my... We did 27 a second ago. This is problem 28. There's one more in the homework problem we haven't talked about, and that's problem 29. So let's talk a little bit about that one. This homework assignment, I should warn you, is probably a little bit longer-winded than most of the homework assignments. Most of the problems kind of take you through it step by step, but it's a little more complicated than some of the other problems. Okay. All right, so problem 29 talks about skin depth, which is a result of Faraday induction. So here's the idea. Suppose you applied a changing magnetic field to the body. So you have the dB/dt that you are applying. We found that a changing magnetic field induces an electric field, Faraday's law. Changing an electric field, multiplied by the conductivity, you get a current. Currents produce their own magnetic fields, Ampere's law. And you end up producing a magnetic field when you apply a changing magnetic field. And if that magnetic field is big enough, it will actually sort of cancel the applied magnetic field, and you'll end up canceling it out and shielding the tissue from the applied magnetic field. It'll only penetrate a distance called a skin depth. So this problem asks you to analyze the equations of electricity and magnetism to get the skin depth. So it involves Ampere's law, that's J to B, Ampere's law, and it involves Faraday's law. What's wrong with that chalk? Faraday's law. And it just laws, this is E and J, this is really Ohm's law. So we're dealing with Faraday's law, Ohm's law, and Ampere's law. So I'll kind of get you started. The problem with some of these homework problems is it's got multiple parts. But the good news is each part is just a small step. So in this problem, you have to use the differential form of these equations. So remember, we found Ampere's law was integral B dot dl was mu naught times J. Or Q naught, I guess, I enclosed. That was Ampere's law we found last class. But you can also use Ampere's law in its differential form. And we looked at that briefly because one of the homework problems. The differential form is curl of B is mu naught times the current density. Completely equivalent ways to talk about Ampere's law, but this is the form, the differential form you're going to want to use. So we'll start with Ampere's law. So all you really have to do is write down Ampere's law. In this problem, if you find yourself doing a lot of numerical calculations, you're probably on the wrong track, because I'm really asking you to do an analysis of the basic equations. Okay, part B. You're going to use Ohm's law. Ohm's law was E is equal to sigma J, which means J is E over sigma, right? So you're going to get del cross B is equal to mu naught, and here's J, so that's E over sigma. So I'm doing a lot of this for you, but I want to get you a good start. The next step in the problem to really analyze skin depth is you take the curl of both sides of the equation. So you take the curl of B. Remember, curl is just a type of derivative. Mu naught over sigma curl of E. Now there is a vector identity that's given to you. Curl of a function, of any function, B, is the gradient of the divergence of B minus the Laplacian of B. That's a vector identity. It's pure math. There's no physics in that at all. Anybody remember what the divergence of the magnetic field is? We talked about it a little bit when we talked about Maxwell's equations. You have a homework problem, scavenger hunt, collect Maxwell's equations. Magnetic fields have zero divergence. What that really means is magnetic fields never start or stop anywhere. They just go around in loops and loop back on themselves. So you end up getting a minus B squared because the first term is 0. Okay. Does anybody remember what Faraday's law is written in differential form? Here's Faraday's law in integral form. It is equal to minus d dt of the magnetic field times the area. Looks a lot like Ampere's law in integral form. The differential form is curl of E is minus dB dt. This is Faraday's law in differential form. So what you do is you plug that in here. Curl of E, you use minus dB dt. Okay, well, now you've gotten something that looks like the diffusion equation. 2 derivatives in space, 1 derivative in time. And it turns out that magnetic fields diffuse into conductors. And the rest of the problem asks you to calculate the diffusion constant and estimate how long it'll take to diffuse in under various cases. So it examines transcranial magnetic stimulation. When you apply with a magnetic stimulator, you're changing the magnetic field in about 1/10 of a millisecond. That seems fast, but the conductivity is small enough that the fusion doesn't matter. The magnetic fields penetrate the body almost instantaneously, and you have hardly any effects of skin depth during magnetic stimulation. Then the problem asks you to look at magnetic resonance imaging, and we'll talk about this next semester if you take medical physics. But magnetic resonance imaging has 3 types of magnetic fields. A static magnetic field. There's no skin depth from static magnetic fields because there's no rate of change. It has gradients that get turned on and off, but they also turn on and off kind of slowly. And then it has a radio frequency magnetic field. That's at what's called the Larmor frequency of the spins. And that's up in the megahertz. So if you put in the frequency and the rate of change that corresponds to the radio frequency magnetic field, you can calculate the skin depth. It turns out the skin depth is still pretty big. If the skin depth is a meter and your head's a couple tenths of a meter, the skin depth's not important. It's only when skin depth happens over just a very narrow length, a small length, that it's important. So it turns out in magnetic resonance imaging, skin depth's not really that big of a deal unless you use stronger and stronger static magnetic fields, which drives the radio frequency up higher and higher. You can actually get where there's a little bit of effect from skin depth. And now, one thing that's not in this homework problem, but I'll give you a little story, is are there any cases where skin depth in the body is important? Well, right now, so this is a little bit of a digression. Right now, they're building a new type of cell phone technology called 5G, 5th generation cell phone. And they're using frequencies that are up around 10, even 100 gigahertz electromagnetic fields. If you go up to that high of a frequency, you can calculate the skin depth, and the skin depth is only a few millimeters, which means these fields don't penetrate into your brain or into your body very far. They really penetrate about the thickness of the skin, so skin depth's not a bad term for that. And they had this town hall meeting in Rochester because there's a lot of people who were worried about the health effects of these 5G radio waves. And I was asked to go and present at it, so I went to this meeting and I started to tell them why I thought there was really almost no danger from these cell phone radio waves. And the people there got very mad at me. And And they started saying no, no, and disagreeing, and we never did come to an agreement. They were convinced that there was health effects. I'm fairly sure, I can't say I can prove it, but I'm fairly confident that there aren't a lot of health effects. And part of the reason is because these fields don't penetrate the body very far. They get essentially reflected from the body, just like you would happen if you reflected from a mirror, because of the skin depth questions. But there's also no other good mechanisms to explain. The only thing they can really do is heat the body through our Joule heating, like we saw, just like a microwave oven can heat the body. But the fields aren't strong enough to do that. So that didn't make it into the problem because that happened just a week or two ago. But there are cases where skin depth can be important, but it's not magnetic stimulation, and it's not really MRI. You have to go up to really high frequencies. Skin depth becomes important. Of course, skin depth in a wire is a lot shorter because the conductivity is 1,000,000 times higher than it is in our bodies. So skin depth in wires happens when you just get up into radio frequencies, but for a body it takes huge frequencies. Okay, so that is a little bit about Faraday induction and its applications in health and in humans. So we talked about biomagnetism, we talked about Faraday induction. That's the end of our discussion of Chapter 8. So hopefully you've got enough to do your homework. Please bring homework questions on Wednesday if you have them. And start reading Chapter 10, and we'll move on and talking a little more about the heart and some of the nonlinear dynamics of the heart starting on Wednesday. All right, so I will see you then on Wednesday.